The Mark II reflector sight produces an illuminated ring with its radius serving as a unit of measurement when laying off deflection. As the diameter of the ring is fixed, the sight can be used for estimating range. Considerable help in precise range estimation is given by the range bars, which appear as an addition to the ring. When these bars are drawn apart by adjusting the base control, the space between them can be made to fit the wider wingspan of a larger target at a given range. Here, for example, is a 60-foot aircraft fitting the range bars at 100 yards. Another adjustment, the range control, allows the range bars to be set so that they will fit a particular size of aircraft at any other range. The illuminated graticule is seen reflected on a sloping sheet of glass, which is a feature of all reflector sights. The reflected image is made by an optical system and lamp built into the body of the sight. This optical system is designed to allow a change of eye position without affecting the direction of the line of sight. Moreover, although the body of the sight appears to grow when approached, the size of the ring remains unchanged. The limit to this freedom of the pilot's eye is reached only when there is just sufficient of the graticule seen reflected in the sight. At night, the graticule should be dimmed to barest visibility to avoid the risk of glare. With its guns fixed to fire in a forward direction, a fighter must be flown towards its target. Given straight and accurate flying, the fighter's bullets converge onto its fore and aft axis at a distance determined by the fixed alignment of the guns. The problem of sighting is simpler to demonstrate with a single gun, aligned to fire directly along the fighter's line of flight. It would be simpler still if the bullets were unaffected by the force of gravity, for they would then continue in the direction in which they were fired. Providing the fighter were then flown in a straight line, these bullets would travel along the fighter's line of flight towards a point which could then be marked for sighting. But flight is rarely straight in combat. Consider the case of a target crossing the line of flight of a fighter which continues flying straight. The period of firing would here be far too short to be effective, whilst the opportunity for shortening the range is lost. To press home his attack on a crossing target, a fighter must turn in to pursue his target and continue on a curve. This curve, the curve of pursuit, introduces the problem of deflection, which is the allowance needed for a turning gun. A turning aircraft has a continual change of heading, whilst the flight path of each separate bullet marks the instantaneous bearing of the gun at the moment it was fired. Because the bearing of the line of sight is changing and the bearing of the bullet path is fixed, they diverge, producing an angle determined by both the fighter's rate of turn and the bullet's time of flight. This angle is the deflection angle, and it presents a source of serious shooting error if allowance is not made. Allowance is made, of course, by aiming ahead along the target's line of flight by the amount of the deflection angle. As deflection is an angular allowance, it may be measured in terms of the radius of the sight ring, which, subtending a fixed angle from the pilot's eye, gives a convenient form of scale. The angle between the fighter's line of sight and the target's line of flight is known as the angle off. At any given range, the greater the angle off, the greater the rate of turn required to follow the target. Therefore, the greater the angle off, the greater the deflection angle. The amount of the angle off is therefore an indication of the deflection to allow. The pilot's only guide to the amount of the angle off is in the appearance of his target. When the target presents its beam to the pilot, the angle off is at the maximum. This is true whether the target is attacked from above, from the same level, or from below. When the target presents an end-on view, it shows the angle off to be at 0. This is a no deflection shot, because the fighter can continue flying straight while maintaining steady aim. Between the two extremes of a large angle off, requiring maximum deflection, and no angle off, requiring no deflection, there is an infinite variety of intermediate stages. Pilots should study the sections of air diagram 2343, which show the appearance of all the important aircraft types at various degrees of angle off. When the angle off is recognized, it is possible to allow deflection according to the target speed. With the angle off at 90 degrees, one radius of the sight ring for every 100 miles an hour of target speed is allowed along the target's line of flight. When the angle off is less than 90 degrees, these allowances are less. As deflection is determined by both the target speed and the angle off, and both are variable, standard rules are given for the average attack. The standard rules assume a normal target speed of 300 miles an hour and state the allowance appropriate to this speed at specified degrees of angle off. Notice that for 10 degrees, the allowance is half a rad, and that for 20 degrees, the allowance is 1 rad. It is obvious by now that in most attacks, the target must be held offset from the center of the sight. This means that there is usually little help afforded by the range bars in estimating range. Range can, however, be estimated in another way. It so happens that the diameter of the sight ring is equivalent to 35 feet, which is the size of a single-engine fighter when the range is 100 yards. When the same type of aircraft is seen to equal half this width, the range is 200 yards. A third of the width, 300 yards. A quarter of the width, 400 yards. Some experienced fighters find additional help in estimating range in the amount of detail they can see in the aircraft they attack.